Disclaimer, this problem is huge. First, we are given a pretty big circuit diagram here, and then in part A we are asked to use the node voltage method to find the total power developed in this circuit. So we need to find the power delivered. After this, we are going to check our answer by finding the total power dissipated in our circuit. So the total power that's going to be delivered is found by using the power formula, and this is voltage times current. So we have our current right here, and we know that our voltage is going to be same over this resistor and this resistor, since they are in parallel, since they are exactly in parallel with each other. That means we have to find the voltage. To find the voltage for one of these, we would just do a plus minus and then have our V1 here. This will find our voltage, and then we could use this, multiply it by our current, and get the power delivered by this current right here. Then to get the power absorbed, we can add all of the current across these resistors here, and we can see the power that's being absorbed by them. For our node voltage formula, this is going to be our voltage 1. We are also going to have a voltage 2 right here, and then we are going to have our unknown right here, this I delta. We're going to need to find that afterwards. To start this problem, I'm going to first look at our V1. So we've done step 1, we've defined both nodes. Now we're going to look at step 2. Step 2, we have V1 minus Vs. This is normally. We don't have a voltage here. In fact, the voltage is going to be the same across this resistor and this resistor as we previously stated. So what this means is that our voltage 1 over our 40 ohm resistor, since we're trying to calculate for the current. We know that our 25 amps is going into our first node, so all of the currents in here are going to have to equal 25 amps when we add them together. So this is our first node, and we can set this equal to a 25 amps because the current going this way is going to have to be added to the current going this way, and that'll all have to equal 25 amps. It's super important to know that, because normally we would have a 0 on the right side of our equal sign. We're going to continue the left side by having a plus here, and then we want our V1 over our R1 because we have to look at this part right here. So we're going to have a plus V1 over 160 ohms. Next to this next part, and to calculate the voltage or the current over this next part, we're going to have a plus V1 minus V2, and this is divided by the resistor between them, which is 10 ohms. Next, we're going to look at our second node. This would be right here. In our second node, we're going to have our V2 minus V1, and this is over the 10 ohm resistor. And then we're going to look at our second voltage, so we're going to have V2 over our 20 ohm resistor plus, and then this part is also pretty important, we're going to have our V2, and then we know that for this the voltage is going this way. However, the current, because of this resistor, is going to be absorbed this way, going into our node. So we are going to have a negative 84 times a I delta, and this is over the 8 ohm resistor, set equal to 0. Lastly, we need to solve for our I delta. We can see that our I delta is right here. So we have our I delta equal to, and then we're just solving for the current here. Current is voltage over resistance, and this is V1 over 160 ohms. Kind of similar to what we would do right here if it was between two resistors. Now we are just going to simplify and add like terms. I'm going to multiply the top by 160 ohms. The second part I'm going to multiply by 40 ohms, and now we're going to go from here. After we do this, we are going to get these two equations right here. Now we notice that in our second equation is the only place where we have our I delta. So we can plug this in, and then we're going to see that we only have V1 and V2. And then we can substitute them and then find each of them respectively. Plugging this part in here, we're going to get a negative 4 V1 plus 11 V2 minus 420 times V1 divided by 160 ohms, and that's equal to 0. I must have messed up on one of the units somewhere, but that's okay. We'll just omit this ohms right here, and we will take this in terms of voltage. I must have had to have a resistor up here to cancel out the resistance, or some way to multiply this to be voltage on the top. Anyways, the resistance on the bottom is not supposed to exactly be here, so we're just going to ignore it for this part. I'm going to get rid of these zeros, and then I'm going to divide 16 by our 42. Doing this, we're going to get a 2.625 V1 here, and this is negative, so we're going to add our V1s together. We're going to get a negative 6.625 V1 plus 11 V2, and that's equal to 0. So when I do this, I'm just going to solve for V1. So I'm going to say that our V1, right, is equal to, and then we're moving the 11 V2 over, but we're getting rid of the negative. So we're going to have 11 V2, and this is over our 6.625. And this is our equation for V1. Now we can just plug it back into the first equation right here. Doing this, we're going to get a 21 times our 11 divided by 6.625 times V2 minus 16 V2 is equal to 4,000 volts. We're just going to combine our V2s and then divide. If we do this, we are going to get that our V2 is equal to 212 volts exactly. So this is the value for our V2. This is going to go right here. Next, we're going to look at our V1. So we're just going to use the same first equation a second time right here. And we're going to do 21 V1 minus 16 times our V2, which we have to be 212 volts, equals to 4,000 volts. If we do this, we're going to get that our V1 is equal to 352 volts. Lastly, we just need to solve for our I delta, and this is this part right here. Our I delta, we just have V1 over 160 ohms, so we're just going to plug in our 352. If we do this, we're going to see that our I delta is equal to 2.2 amps. Now we found our voltages and we found our delta. Now we need to find the power absorbed and delivered. Now that we know the voltages, we can do that. We also should note that this voltage is the same across here, and we can easily find any other voltages across these resistors. So first is the voltage delivered. Now the voltage delivered is going to consider this initial current, this source current, and it's going to consider the source voltage. Well, we know the source voltage is going to be the voltage that it starts with, and that's going to be this V1 right here, since it takes place at the start of our circuit diagram. So when we calculate for power, we're going to have our P is equal to, and this is the power formula, voltage times current. Our voltage for V1 is 352, and this is being multiplied by our current, which is 25. Also, this is volts times amps, which gives us watts. And this is going to give us a power delivered of 8,800. Since it's delivered, we have to have a negative out front. This is our answer for the first part. And for power absorbed, it's just going to be the opposite. It's absorbing the same amount of power if it's a perfect circuit. This will be 8,800. However, it's important to also check this. In fact, the answer tells us to check the answer by finding the total power dissipated in our circuit. And it's dissipated because the resistors absorb the power. There's a couple of different ways to actually use the power formula. We have a couple of different variations of it. We first have power is equal to voltage times current. We also have power is equal to current squared times resistance. And then we also lastly have power is equal to voltage squared divided by resistance. And these are the different formulas we're going to be able to use. So to start this off, we're going to calculate the power for each individual part of our circuit diagram. First, we're going to start with here, and I'll check mark each of them as we do it. So we have this 84 times our I delta voltage right here. Well, we're going to need either a resistor or current. We can't just make up a resistor for here, so we're going to need to find the current for this. The way that we're going to find the current for this is by using the current formula. I think this is Ohm's law to be specific, but basically we're going to be finding the current that's flowing through this way. Also note that it's asking us for the total power, so we're going to have to add all of the power for the individual circuit diagrams together. Well, we need to find the current that's going in here to begin with. So to find the current going in here, I'm going to do this on the far right side. We know that our current is equal to, and then we're going to actually just use this equation right here. The voltage 1 In this case, that's going to be V2 minus our voltage 2, and in this case, it's going to be our 84 times our I delta. We know that our I delta is 2.2 amps, and we know that our V2 is 212 volts. And this is all over the resistor between them, which is 8 ohms. So if we do 212 minus 84 times 2.2, and then divide this by 8, we're going to get that our current is equal to 3.4. That means that the current flowing through here is going to be 3.4. This current right here that we listed is 3.4. So in here we're going to have our voltage, which is just 84 times our I delta, which we know to be 2.2, times our current, which we just found to be 3.4, and that's it for the first part. We're going to add to this the next part over this 8 ohm resistor. We know the resistance for this, and since we know that the actual current flowing through from this node to here is in series, that means we can reuse the current that we found right here. We can reuse this because in series the current flowing through is the same. So over our 8 ohm resistor, we are just going to have a 3.4 and then raise this to the second power as per the formula, and this is being multiplied by the resistor itself, which is 8 ohms. Next, we're going to look at this 20 ohm resistor down here. We know the voltage that's flowing through here. We just found that out to be 212, and we know the resistance. So we're going to have our 212 raised to the second power, and this is being divided by our 20 ohm resistor. Next, we're going to look at this 10 ohm resistor right here. So we have our resistance right here. We don't know the voltage flowing through it. The easiest thing to do here would just to be to find the current flowing through it. And we can use the same formula that we've done twice over now. We can say that our I, and we'll call this of the 10 ohm resistor, and I'll actually just label this other one as the 8 ohm resistor, just to keep things nice, is equal to our V1 minus V2. Well, we know our V1 to be 352 volts, and this is being subtracted from our V2, which is 212 volts. This is over the resistance between them, which is 10 ohms. And so we're going to get that our I of 10 ohms is equal to 14 amps. Plugging this into our power equation, we have 14 squared, and this is being multiplied by the resistance, which is 10. Now we move on to the next part where we have this 160 ohm resistor. We know our V1 as 352. We also know the current flowing through here as our I delta, and our I delta is 2.2. So we'll multiply this by 2.2. Lastly, we are going to look at our 40 ohm resistor right here. We know the current flowing through our 40 ohm resistor to be 352 since our V1s are in parallel. So we'll have 352 raised to the second power, and this is going to be divided by our 40 ohm resistor. If we do this, we can see that we get an 8,800. So we've checked our work. We know that our current is perfect, it's exact, and this is how we solve the problem. There's a couple of different ways how we can write or explain how we got to some certain things, especially for the power formula or how we wrote out the nodes, but this is the way I find the easiest to go over and understand, and I hoped it helped. So if you want more problems like this, there's a playlist linked below that covers all the basics of circuit analysis. There's also notes linked below that will help with all of these problems as well as studying for an exam.